Hello everyone. I hope everyone is fine and doing well. Well, this is the first video of the online lecture series on the subject of power electronics, which is being taught as a breadth course in the Bachelor of Electrical Engineering curriculum at DH Sufa University, Karachi. Today I'm going to start this lecture series from the review of the concepts of one of the fundamental power electronic devices known as Thyristor. Thyristors are also known as silicon controlled rectifiers. So these two terms are going to be used interchangeably for the same device. I hope this will not put you in confusion. We already discussed what power electronics is in the previous lecture that was held in class. Let me recall you once again. The power electronics is actually the control and processing of electrical energy using semiconductor switches and energy storage elements, which include inductors and capacitors. Power electronics is an enabling technology. It enables other technologies to function. It is definitely a growth area, and it has a vital role to play in energy efficiency. Well, power electronics actually deals with the applications of solid-state devices for the control, conversion, and processing of electrical power. Conversion techniques require switching, which means on and off of power semiconductor devices. I already told you that the basic elements which make up the power electronics are called power converters, and power converters are actually used as interfaces to match the supply characteristics to the load characteristics. This is the basic aim of power electronics. So moving on to the main topic of discussion, which is thyristors. Today I will be discussing with you the basic structure and the operation of this power semiconductor device, as well as the static characteristics, which includes the current and voltage curves. Generally speaking, thyristor is a name which has been given to a family of power semiconductor devices, and these devices include silicon control rectifier, triac, which we will be discussing later on, diac, silicon control switch, gate turn off thyristor, reverse conducting thyristor, and programmable unijunction thyristor. But thyristor is more commonly used for this semiconductor device known as the SCR. This power semiconductor device is a bistable switch, which means it blocks the voltage and current both in the reverse mode as well as in the forward mode, and it operates from non-conducting state to the conducting state by the application of a gate signal. It will not be wrong to say that since a thyristor is a PNPN device, it belongs to a transistor PNPN or NPN device family. But compared to transistors, thyristors have low on-state conduction losses and higher power handling capability. However, transistors have faster switching speed as well as lower switching losses. You can see from the figure 1 and figure 2, which provides us the constructional view as well as the schematic, the thyristor has 4 layers of p-type and n-type semiconductor materials, along with 3 junctions named J1, J2, and J3. The 3 terminals of the thyristor are known as anode, cathode, and gate. You are already familiar with the diode. Diode has 2 terminals, anode and cathode. However, Thyristor has got one additional terminal which is known as gate. As we can see from this figure, which is providing us the constructional details of a thyristor, the threaded portion is for the purpose of tightening the thyristor to the frame or heatsink with the help of a nut. You can see that the gate terminal is usually kept near the cathode terminal. The terminal connected to the outer P region is called the anode. The terminal connected to the outer N region is called the cathode, and the one connected to the inner P region is called the gate. For large current applications, thyristors need better cooling. This is achieved to a great extent by mounting them onto the heat sinks. You can see that I have mentioned in the slide that a typical SCR rating would be like 10 kV, the power handling capability of 30 megawatt, and an RMS current rating of about 3000 amperes. Such a high power thyristor can be switched by a low voltage supply of about 1 ampere and 10 watts, and you can see this gives us an idea of the immense power amplification capability of the thyristors. Since they are solid state devices, they are compact, they possess high reliability, and therefore they have very low losses. A thyristor is called SCR, which means silicon control rectifier, because silicon is used for its construction, and it operates as a rectifier, which means very low resistance is offered in the forward conduction mode and very high resistance in the reverse conduction mode, and it can be controlled. Like a diode, it is a unidirectional device, which means it blocks the current flow from cathode to anode. And unlike a diode, it also blocks the current from anode to cathode unless triggered by the application of the gate signal. Now moving on to our next topic, which is to study the static VI characteristic of thyristor. I would simply put it, it is actually a graph between the voltage applied across the device and the current flowing through the device. This curve provides us valuable information about the operating region of the component. By studying the static VI characteristics, we can understand where and how to use a component in electrical circuit. It depicts the behavior of the device for various values of the applied voltage. Here, an elementary circuit diagram has been shown, which can be used to obtain this static VI characteristic shown in the figure 4. As you can see, the anode and the cathode have been connected to the main source of voltage through load via a variable resistor, so that we can control the anode current in the forward biased mode. The gate and cathode terminals are also connected via another source of voltage known as ES. From the figure 4, you can visualize that a thyristor has three basic modes of operation. One is the reverse blocking mode, the other one is the forward blocking mode, and the third mode is the forward conduction mode, also known as the on-state mode. I'm going to discuss with you these three modes of operation one by one. First is the reverse blocking mode. In the reverse blocking mode, the cathode is actually positive with respect to the anode, and this happens when we apply a reverse voltage across the thyristor. Now in this situation, out of the three junctions, junctions J1 and the junction J3, they get reverse biased. However, the junction J2, it gets forward biased. Now what happens is the thyristor actually behaves as if two diodes have been connected in series with reverse voltage applied across them. I would like to mention over here in the figure that a small leakage current of the order of few milli or microamperes flows through the thyristor depending on its rating. The SCR over here is said to be in the reverse blocking mode, also known as the off state. Now, if this reverse voltage is increased, then at a critical value known as the breakdown value, an avalanche occurs at the junctions J1 and J3, and the reverse current increases rapidly as it can be seen in the figure. Now, a large current associated with this breakdown value of the voltage, it brings more losses in the SCR. This may also damage the thyristor as the junction temperature may exceed its permissible limit. You must note that the maximum reverse voltage should not exceed this breakdown value. Apart from this, we can see that when the value of the reverse voltage is less than VBR, the thyristor offers very high impedance in the reverse direction. Putting it simply, it is blocking the flow of current in the reverse direction. The curve which has been shown in the figure, it is actually obtained when the load resistance is 0. Now, in case if there is some load resistance present, a large anode current associated with this breakdown value would cause a substantial voltage drop across the load, and as a result, in the third quadrant, the curve would bend to the right of the vertical line like this. The curve would be slightly like this. I hope it is clear to you people. Now, now coming on to the next mode, which is the forward blocking mode. In this mode, anode is made positive with respect to the cathode, as can be seen from the polarities of the supply voltage. The junctions J1 and J3, the outer junctions, they are forward biased. However, the middle junction, the inner one J2, it gets reverse biased. You can see from the figure a small leakage current known as forward leakage current is flowing when the thyristor is in the forward blocking mode. Now, if we keep on increasing the value of this forward voltage up till VBO, which is known as the breakover voltage, the middle junction it will break down due to an avalanche if we are going to exceed this breakover value. Behind this breakover value, whatever the value remains of the forward voltage, SCR would be offering high impedance similar to when it was offering in the reverse blocking mode. Hence, it can be treated as an open switch in the forward blocking mode as well. Now, if you would like to bring the SCR from the blocking mode to the forward conduction mode, there are two methods. Either you exceed this breakover voltage, in which the gate current will suddenly increase in value, as can be seen from the curve, or the middle junction J2, which is reverse biased, it can be made forward biased by applying a small gate pulse between the gate and the cathode. There are two currents known as the latching current and the holding current, which we'll be discussing later on when we'll be discussing the dynamic characteristics of the thyristor. Let me just tell you that the voltage drop across the thyristor in the on state will be of the value of 1 to 2 volts depending on the rating of the SCR. In the conduction mode, the anode current is actually limited by the load impedance. As you can see, when the thyristor is in the conduction mode, the voltage drop across SCR is quite small. This voltage drop across the device is due to the ohmic drop in the 4 layers. What I have just discussed with you, I have summarized in bullet points so that you can later on